Good morning to all of you. In previous class we discussed about the magnetic properties of the matters, where we discussed about the diamagnetism and paramagnetism, and then we'll discuss about the ferromagnetism and ferrimagnetism materials. And then we discussed about the relation between the magnetization vector and magnetic field intensity and magnetic flux density B. And the relation we found, B is equal to mu naught H plus M. But the mu naught was nothing but the permeability of the free space. Then we found another relation, mu naught 1 plus susceptibility is equal to mu, where the mu is nothing but the permeability of the medium, absolute permeability of the medium, and the mu r is basically 1 plus susceptibility. So on the basis of the permeability and susceptibility, we also distinguish between the diamagnetic material, paramagnetic material and ferromagnetic materials. Today we are going to discuss about the MH2. Means when you apply the magnetic field on any magnetic material, then that material, how it is going to respond with respect to external magnetic field. That will actually exhibit one curve. That curve is called as MH2. So before understanding the MH2, first we'll talk about the domains. What are the domains? So in the previous class we discussed about that the magnetic moment in the lattice, they start to interact through the exchange energy, exchange interaction, and they try to align in a particular direction. So if you look into the bulk materials, then there is a localized region in the material. They have some magnetic moment in a particular direction. Okay, so if I draw a small piece of pictorial diagram of a small piece of bulk magnetic material, there will be some localized regions where the magnetic moment will be aligned in a particular direction. So let me take, there are few regions. Like this. The magnetic moment in this region are aligned in this direction. They are will be in this direction, like this, like this. So there are different reasons where the net magnetic moment is not equal to 0. So if you look only this region of the material, then there is a net magnetic moment, and in this region there is also some magnetic moment, and in this region there is also some magnetic moment. But overall the magnetization of this specimen is equal to 0 in the absence of external magnetic field. Basically here we are talking about the ferromagnetic material. So applied magnetic field H is equal to 0, then the magnetization is equal to 0. Overall the magnetization of the specimen or the sample or the material is equal to 0. But when you apply the magnetic field, these domains or these magnetic moments of the localized region will start to align in the direction of external magnetic field. Alright? So these all the reasons where the net magnetic moment exists because of the interaction are called as the domains. And these domains are separated by some boundaries, and these boundaries are called as magnetic or domain boundaries, and also called as a Bloch wall. So what is exactly happening at the region of the Bloch wall or domains wall? So if I consider there are two domains, one is aligned in this direction and second is aligned in this direction, opposite. The magnetic moments in these two domains are aligned in the opposite directions. So there is some boundary that is called as a domain boundary. Okay, and the magnetic moments are reversed in each domains. So exactly what is happening at the domain boundaries, the magnetic moment will flip from upside to the downside. Here in this specific pictorial representation, the magnetic moment from the one domain will start to flip in the second region, and this is not abruptly. This is going gradually from one region to another region at the domain boundaries. So if I zoom this region, if we try to understand what is exactly happening at the domain boundary. So in the let me say this is the domain A, this is the domain B. In the domain A, the magnetic moment is upward. As you start to travel in the domain, this magnetic moment start to flip. And after certain distance, okay, within this domain region, it will reverse from up to downside, okay, as represented in the domain A and B. So this region where the magnetic moment flip from one direction to another direction is called as a domain boundary. So this is how exactly happening in the bulk material. Okay, so when you prepare any magnetic materials, so these domains will create inside to minimize the magnetic anisotropy energy. So this portion you will study in the solid state physics in the 5th semester, and here we will take the overview of the MH loop on the basis of the domain theory. So first I simply explained about the domains. So the domains are nothing but a localized region within the specimen where the net magnetization is not equal to zero. They are magnetic domains, magnetic moments interact to each other, and they try to align in the one direction to minimize its magnetic energy. And this happen at each and different points in the specimen, and they create their boundaries. They create their regions, and because of those regions there is some boundaries. So these boundaries are called as a domain boundaries, or you can say the Bloch wall, and you will study in the detail in the solid state physics. Here the main concept I explained to you, that is nothing but the domain. Now on the basis of the domain, I am going to explain the MH curve. So let me take the applied magnetic field along the direction of the x, and will record the magnetization of the material and will plot along the direction of y. Let's say this is the m. So when the magnetic field is zero, this H is a magnetic field intensity, this is a zero. You have taken this specimen and you applied the magnetic field from the outside. Okay. So how it is going to respond? So when the magnetic field is zero, let me take this is nothing but origin. So when the magnetic field is zero, so all the domains are randomly oriented. They are like, as we discussed here, they are randomly oriented. Like this. Okay? As we start to increase the external magnetic field, these domains will try to align in the direction of external magnetic field by taking the energy from the external magnetic field. So first they will increase like this, and after certain time, after certain magnetic field, external magnetic field, all the magnetic domains are aligned in the direction of all the probable domains align in the direction of external magnetic field. So at this situation, you can see here at this particular external magnetic field, there is no increase into the magnetization with the further increase into the external magnetic field. So what is exactly happening at this point? Where all the domains which are present in the specimen are aligned in the direction of, all the preferable domains are aligned in the direction of external magnetic field. Alright? At this point, all the domains are aligned in the direction of external magnetic field. So there is no further increase into the magnetization because there is no other domains which are left to align in the direction of external magnetic field. So there is no further increase into the magnetization with the increase of the external magnetic field. And this point is called as a saturation. Okay, and the magnetization which you received at this point is called as a saturation magnetization. If I draw a line which cut the y-axis perpendicularly, this point is called as a saturation magnetization, MS. Okay, it's called MS. Now, after that, when you start to decrease the external magnetic field, you reach up to the certain magnetic field where all the domains align in the direction of external magnetic field. After that, you start to decrease the external magnetic field. Then they are not going to follow its own path. So this process is basically irreversible. What is happening? When you remove the external magnetic field, stepwise, slowly, then all these domains are not coming back into the original state. The sum of magnetic domains are still aligned in the direction of the external magnetic field which you applied earlier. Okay? So they retain some magnetization because of the external magnetic field when you applied at that time. Okay? So this portion where, this point where the curve cut the y-axis is called as a retained magnetization, or this point is called as a retentivity and represented by an R. Okay. After retaining, means this material is going to retain some magnetization. Now if you apply the magnetic field in the opposite direction to remove the retained magnetization from the specimen. So now this time I am going to apply the magnetic field in the opposite direction as we applied earlier in the positive x-axis. Now we are applying the negative x-axis in the opposite direction. So after certain value of the magnetic field, all the retained magnetization in the specimen, all the domains which are still aligned in the direction of external magnetic field, now they are going to realign, or they are going to adjust themselves so that the retained magnetization becomes zero. At this external magnetic field, at this point, all the magnetization in the specimen which was retained, now it's become zero. And this point is called as a coercivity which cut x-axis. Coercivity sample or specimen. Now, you further increase the magnetization in the opposite direction, then your specimen will start to align in the opposite direction. So all the domains now start to align in the opposite direction. Now after a certain value of the external magnetic field, the domains now further align in the negative x direction, I would say here. At this magnetic field, you can see there is no further increase into the magnetization with the applied of external magnetic field. Now it is again attained the saturation point. So at this point, other magnetic moments, other domains all are aligned in the opposite direction, where you applied the magnetic field, in the direction where you applied the magnetic field. Now this is also called as the saturation point. Sometimes also represent this as a ms. Now again we decrease the applied magnetic field. It will intersect this point, obviously. Okay, again it will retain the some magnetization, but this time this is in the direction of applied magnetic field. Obviously the applied magnetic field was in the negative x direction, let's say, so the magnetization retained by your specimen is in the negative x direction. Now again you apply the magnetic field in the direction, positive x direction. To remove this retained magnetization from the sample or a specimen, then you have to apply the some magnetic field to remove this magnetization. So at this magnetic field, again the magnetization retained by the sample will become 0. The further we increase the magnetic field in the positive x direction, and it is going to like this. Again it will get the saturation states. Again all the domains at this field, again all the domains will align in the direction of external magnetic field. So this is the process which is happening when you apply, when you expose the specimen, magnetic specimen, especially I am talking about the ferromagnetic material, in the presence of external magnetic field. Okay, so I started from the zero magnetic field. First it is going, all the domains are going to align in the direction and it becomes saturate. Okay, this is called the saturation magnetization. Whatever the magnetization retained by the sample, when you remove the external magnetic field, that has become 0, and the retained magnetization is called as the retentivity. And if you want to remove the retained magnetization from the sample, you have to apply the magnetic field in the opposite direction. And the required amount of external magnetic field to remove the retained magnetization from the sample is called as a coercivity. And the further increase into the external magnetic field in the negative x direction, let's say, then there is again the saturation will happen. Means all the domains now again align in the applied magnetic field. It again becomes saturate, and then again if you remove the external magnetic field, now its external magnetic field becomes 0. At this point it's again there is some retained magnetization in the specimen, but in the opposite direction. Earlier was in the positive y-axis, now there is a retained magnetization in the negative direction. Obviously that is in the direction of applied magnetic field, but this is only the representation. Okay, and if you want to remove the retained magnetization, then you have to apply the magnetic field in the positive x-axis and further increase into the external magnetic field, it will become straight. Okay, so this is going to represent by a curve. This curve is called as a MH loop, and the sometime you also plot the BH curve. As we know, there is a B is equal to mu naught H plus M magnetic. Alright, so even you can plot the curve B and H. If there is if you want to calculate the value of the total magnetic flux density, then you can plot the curve P and H. So same kind of response you will record even in the case of the BH loop, and similarly you are getting the MH loop over here. Now, so there are a few points I would like to discuss. The most important point first, in the starting, when you are increasing, when your sample, earlier the sample was not exposed in any kind of external magnetic field, and you started from the zero magnetic field, the response between the M and H was near about linear response. Okay, the response between M and H is near about linear. So that, as we know, M and H are related. The linear relation between M and H is this. M is susceptibility into external magnetic field. So from here, if you find out the slope in this initial region or very small external magnetic field, this is called as nothing but the initial susceptibility. Okay, and the physical significance of susceptibility is how easy to magnetize or how hard to magnetize any magnetic material. And after that, this behavior becomes non-linear. So basically, MH curve is a non-linear response, and which simply represented by a loop or exhibited by a loop, that is called as a MH loop. So any question up to this point, class? You want to ask any question?